Hello, everyone. I'm Isaiah Spring. I'm really excited to be here with you guys and share what I've been working on. Here we have, I'm going to talk about the microstructures that we analyzed in Dunite class D1 from Lunar Meteorite NWA 11421 and discuss physical constraints that these analyses provide for its excavation from the lunar mantle. Yes, so this class D1 is the first lunar sample which can be reliably traced to the lunar mantle, making our analysis of it groundbreaking for the lunar sample community, as it is the very first chance we have to begin observing physical and chemical parameters related to the lunar mantle. Here's a cartoon I drew to show this model we have for the lunar interior, which provides for some amount of overturn and some other processes that we have become prominent in that they can explain lots of observations we've made, including observations of the lunar surface, which include this plagioclase flotation crust and various volcanic features. However, these models have yet to be verified by any kind of direct sample evidence. And so as we work on these, we can begin to verify these models and provide the initial data points to really start refining these models. As we better understand the lunar mantle, this is very useful to better understand other terrestrial planets and the early Earth, see how those processes might have played similar roles here and on other planets. Talking about the sample, here is could I go back one? Here's a phase map that we took of a thick section of the sample. You can see it's primarily olivine, minor amounts of plagioclase and pyroxene. Alan Trayman used these two pyroxene pairs to calculate various thermal barometers. All of these kind of are concordant to a depth of 88 kilometers, which places the sample well within the lunar mantle, which is what makes the sample so exciting, like I've been saying. Additionally, I'll point out this temperature he calculated of 980 degrees. Our primary objective with this sample is to begin understanding its trace and minor element chemistry. However, before we got onto that, we wanted to first understand what the deformation state of the sample was and maybe identify possible sources of chemical alteration that may have occurred during its excavation. So for that, we performed an electron backscatter diffraction analysis, or EBSD. EBSD as a method allows us to observe the various orientations of individual grains within the sample and begin to observe what deformation state they may be in. So here's the results of that EBSD analysis. You can see this very colorful map of the sample where we can see orientations of individual olivine grains relative to the sample surface. I've additionally thrown up here some pole figures showing the distributions of those orientations, specifically for each of the three crystallographic axes of olivine. You can see there are increased frequencies in each of these three pole figure plots, meaning that D1 is preserving some sort of preferred orientation, meaning the olivine grains are slightly aligned in a single direction as opposed to being in a random orientation, which we might expect in a more pristine igneous sample. However, in order to really use this data to understand better our upcoming trace element analysis, we wanted to quantify this shock effect. Luckily, the deformation mechanics within olivine have been heavily studied, and various metrics have been developed to help us quantify aspects of this shock event. First, using a EBSD parameter called grain orientation spread, or GOS. GOS is a measure of the mean misorientation between uncorrelated points within a single grain and has been accepted as a pretty good proxy for the general deformation within a single grain. Additionally, the mean GOS for grains larger than 50 microns has been shown to correlate well to the weighted shock stage in experimentally shocked olivine. Weighted shock stages are intervals of increasing shock pressure, which are delineated by the appearance of different optically visible shock features. Ruzicka et al. Created this interesting relationship using the weighted shock stage and mean GOS of chondritic olivine in order to relate the two to each other, allowing me to estimate the weighted shock stage of my sample using this relationship here. With that, I estimated a shock stage of 4.1, which corresponds to a shock pressure of 15 to 20 GPa. This GOS map that I'm showing here shows, of course, the various different values for each of the grains, but it also records thousands of small rotations within these olivine grains. the axes of these rotations, interestingly enough, orient themselves preferentially at different temperatures. I'm going to show you here. This is an inverse pole figure on the left of the crystal rotation axes within olivine relative to the crystallographic axes of olivine. And you can see this increased frequency at the bottom of the plot at the 100 axis, which increases as we move up to the 010 axis, and then, sorry, it decreases as we move up, and then again decreases as we move over to the 001 axis. This pattern is created because the slip systems that operate within olivine activate differently at different temperatures. So this diagram on the right kind of illustrates how that happens. So at low temperatures, around 700 degrees or lower, we will see orientations of rotation axes at the bottom of the graph. This corresponds to what's called C-type slip. As we increase the temperature, we move up and over. This corresponds to the activation of what's called A-type slip. And then at higher temperatures, around 900 degrees, A-type slip becomes the most common. And so using the relative proportions of these different slip systems, Rizika et al. Created this other relationship here, relating the temperature of deformation to the proportion of those different slip systems in chondritic olivine. I was able to use this to estimate a shock temperature of 723 degrees. This is notably lower than the equilibrium temperature that was estimated with the thermobarometry. And we take this to mean that the thermal effects related to the excavation of the sample were likely minimal. This bodes well for our upcoming trace element analysis because the elements that we're specifically interested in are less likely to behave mobily at these low temperatures. And so this was kind of the main results that we wanted to get out of this. What's great about this EBSD analysis, though, is there are other additional interpretations we can make using this data, and I want to talk about just one of those today. I'll get the slide to show over. Okay, so here's a map of the moon where I have highlighted different basins which are believed to have excavated mantle material. Given that our sample is from the mantle, it makes, it follows that it came from maybe one of these different basins. Now that we understand different aspects of this shock event that excavated it, it's our hope that we can try to pinpoint maybe a region of the moon which is the most likely source for our sample. I hope to do this by using various physical features of these basins, as well as the numerous computer models which have been generated for their formations. I'll talk just about one of those here. So here's a plot I've put up to kind of illustrate how this process might work. This plot, we have the peak shock pressure on the y-axis and the peak temperature of the shock on the x-axis. I've made a little field in green to denote our sample D1, and then I've taken modeled ejecta tracer data from Citron et al. And plotted that next to it. We can see that these tracers, which I specifically chose ones that came from the same depth within the lunar mantle, many of them experience similar shock pressures here at the bottom of the graph, but they all pretty much all experience higher shock temperatures, some of them much higher. We take this to mean that the SPA forming impact was likely too energetic and produced too high of a thermal effect on these mantle samples. Because of that, SPA maybe is less likely to be the source of this sample. This is not definitive, of course. At this point, we're still comparing lots of data from many different basins. I just wanted to illustrate how this might work. And in the end, we hope to be able to say perhaps one region of the moon more likely than the other, which will, of course, make our upcoming trace element analyses much more useful to the community, given that we know the moon has a good amount of dichotomy from the near side and far side. And so being able to say that this is a piece of far side mantle or near side mantle greatly increased the interpretive abilities of our upcoming chemical analyses. So in conclusion, I just want to reiterate, D1 experienced this high pressure, low temperature shock event. We think this bodes really well for our upcoming trace element analysis that I'm performing with Jacob Cetera at NASA Johnson, which will hopefully be done real soon, and I'm excited to dive into that. Meanwhile, we're continuing to compare different basin data from these different basins I showed you to try to see if we can't pinpoint the source of the class. I guess I'd just like to acknowledge then funds from NASA, which made this project possible, as well as the contributions of Timmins Erickson at NASA Johnson, my advisor, Ananya Malik, and of course, Alan Trayman at the Lunar Planetary Institute. Thank you.